Welcome back to Differential Equations. In this video, I want to introduce you to the partial differential equation, or PDE. Up until this point, all of the differential equations we've dealt with have dealt with ordinary derivatives of a function of a single variable. A partial differential equation, as its name suggests, deals with the partial derivatives of a function of several variables. So, we could have a function u of x and y, but more commonly we're going to have u of x and t. If you continue onward in your study of partial differential equations, partial differential equations of functions of more than two variables are actually very common. Trying to describe the space we live in, you need three spatial directions and time. X, Y, Z, and t. So partial derivatives or partial differential equations of functions of four variables do exist. But we're going to stick with one of these two cases for our purposes in this course. It makes things easy, and once you understand the basics, it really does expand very readily. The other convention we're going to use that I kind of mentioned there, whenever we're dealing with an x or a y, we're going to think of that as being a spatial dimension, and we'll think about t as being time. So, if I want to take the partial derivative of u with respect to x, I'm usually going to write it using the fractional notation, but every now and then I'll write it using the subscript notation u sub x, especially if I want to emphasize that it is a function or evaluated at a specific point. And then if we wanted the second one, the second partial derivative of u with respect to x, we would write like that, or in subscripts it would be u sub double x. And we can also take time derivatives. One of the first things that I want to point out here is that you should remember from your study of multivariate calculus that mixed second partial derivatives are a thing, right? The partial of u with respect to x and t. We're not going to deal with any mixed partial derivatives in this course. Not that they don't exist, not that they can't show up in differential equations, but as a preview of things to come for anyone who continues on their study of differential equations, it turns out that most of the theory of differential equations is just trying to figure out whether it's possible to solve the partial differential equation or not. Literally, at the time that I'm recording this video, there is a $1 million bounty on determining whether a particular equation called the Navier-Stokes equation has a solution. Not finding the solution, determining whether it always has a solution. Or, barring that, determining what conditions it takes to put on the equation to ensure that it has a solution. The Navier-Stokes equation is a very interesting equation that is core in the study of fluid dynamics. So clearly, in some cases, it has a solution because we use it to model fluids all the time. But it's not clear whether it breaks at some point in the ways that you can use it. And so studying just does it break is still an interesting open question, let alone finding solutions and using them to model things. So there's a lot of room in differential equations for some very interesting questions that are not just go through and do all of the crunching. Most of that theory comes down to trying to model a differential equation in one of the three canonical forms. We have the heat equation, which is written canonically as the partial of u with respect to t is equal to some constant that we usually write as alpha squared times the second partial of u with respect to x. We have the wave equation, which looks kind of similar, but instead of the first partial, it's going to be the second partial of u with respect to t is equal to some positive constant times the second partial of u with respect to x. And then the third canonical form is known usually as Laplace's equation. And this is the one that generally we write dealing with only spatial dimensions. So it's going to be the partial squared of u with respect to x plus second partial of u with respect to y is equal to 0. And the study of differential equations, by and large, is trying to classify the differential equation that you are looking at as a parabolic equation, which means that it can be rewritten to look like the heat equation, or a hyperbolic equation, which means it can be rewritten to look like the wave equation, or an elliptic equation, which means it can be rewritten to look like Laplace's equation. That sort of classification is well beyond the scope of this course. In this course, I really just want to focus on, let's look at these three equations and make sure we understand how they work. Because again, moving onward, looking at something more complicated is going to be trying to turn it into one of these three, and then if you already know how it works, you already know how it works, you don't have to do anything else. The other thing that I want to look at with these equations is that because there are both spatial and time derivatives involved, it is usually the case that we have both boundary conditions and initial conditions in order to take the general differential equation and turn it into something that has a specific solution. And once again, determining what kinds of initial and boundary conditions can go with what types of equations in order to ensure that there are solutions is a much more challenging problem in partial differential equations than it was in ordinary differential equations. We're going to sidestep most of that challenge and just assume that things are going to work out for the equations that we are looking at. Right? For the three canonical forms, if you have boundary conditions or initial conditions that match the constraints in the equation, it usually works out. So if you have a first derivative with respect to time, then you usually need one initial condition, which is going to be something like u of x and 0 is equal to f of x. If you have a second derivative with respect to time, then you're going to need a second initial condition. That's usually going to be something like u prime of x and 0 equals g of x. And right away, you start to see why partial differential equations are so challenging. Because when you set time equal to 0, you still have a variable. So the results that come out of this are themselves functions. And then we usually want our boundary conditions, which is usually going to be something like u of 0 and t and u of some L and t. You can have these equal to the same thing. You can have these equal to different things. You can talk about the derivative, right? So ux of 0t and ux of lt You can talk about combinations of them. There's a lot of room to grow here, and this is where a lot of the complication comes in trying to deal with the partial differential equations. Together, this mix of a differential equation with initial conditions and boundary conditions is referred to as an IBVP, initial boundary value problem. Can't be just one or the other, it has to be both. And yes, our initialisms continue, and it does turn into alphabet soup if you're not paying close attention. I just realized I glossed over this, but when I talked about the boundary conditions, you can see that I put in a constant value, in this case specifically 0. Technically, these should be functions of time. And once again, if you want to look deeper into the theory of partial differential equations, there's a lot to uncover there. But for our purposes, we're going to simplify things and assume that the boundaries are held constant for all time. That makes things solvable. But before we can even think about initial and boundary conditions, we have to think about the equations themselves. And, well, these equations look kind of ugly. There's about the simplest partial differential equation that I can think to write. Partial of u with respect to t is equal to the second partial of u with respect to x. And none of the tools that we have that we've talked about previously are going to do anything at all to this differential equation. So the new technique is one of those things that feels like a magic box the first time you see it. It is called separation of variables, but it has very little to do with the separable differential equations that we solved earlier in the course. Instead, the idea of separation of variables is that we're going to assume, with absolutely no justification whatsoever, that u of x and t is equal to some function big X of x multiplied by some other function big T of t. We have no reason whatsoever to think that this will work, except for the reliance on someone at some point in the past tried it and was able to get a solution. What we are going to do is rely on those existence and uniqueness theorems that I've talked about. I don't have anywhere near enough time in this course to prove to you that for the canonical forms of partial differential equations, solutions do exist. But we can take that result on faith for right now in order to get to the fun stuff. A solution to this partial differential equation exists. The solution to the initial boundary value problem involving this partial differential equation is unique. And so, if any method gives us a solution, that will be the unique solution and we will have solved the problem. That is such a backwards way of thinking compared to the mathematics that you have thought of up until this point in this course or in general in mathematics. I know that when I was a student, that took me years to digest and accept. And by years, I mean I waited until I took the next course in partial differential equations and I actually proved that theorem. And then I started to believe that this was a thing that I could do. Right, but we're going to take it on faith because proving that theorem is going to take me something like 5 weeks of classwork and introducing background information that we don't have right now. And we're nearing the end of this course, so let's just get on with it. Right, we're going to assume that this function exists and that this is the form of a solution. And then from that assumption, we're going to say that the partial of u with respect to t. Well, with respect to t, x of x is a constant. It's a function of x, not of t. Big T of t is a function of t, so we'll need the derivative of big T of t. Likewise, the partial of u with respect to x will be x prime of x times t of t, because x of x is a function of x, t of t is constant with respect to x. And then the second partial of u with respect to x will be big X double prime of x times big T of t. And when we substitute those things into our differential equation, we get x of x, t prime of t equals x double prime of x, t of t. All right, that doesn't look like much, but now we can do a little bit of manipulation. If I divide both sides of this equation by u, that is by big X of x times big T of t, then the x of x will cancel on the left-hand side, and I'll have t prime of t over t of t. And the t of t will cancel on the right-hand side, and I'll have x double prime of x over x of x. That's very similar to the separable differential equations. That's why they have such similar names. So there is some relationship there, but it's not a very strong one. But at this point, we have a very fascinating result. The left-hand side of this differential equation is a function of t, not x. The right-hand side of this differential equation is a function of x, not t. So if I change x and leave t alone, the right-hand side could change, but the left-hand side cannot. It will be constant. Likewise, if I change t but leave x alone, the left-hand side might change and the right-hand side is stuck as a constant. Well, you can't have that. You can't have part of an equation changing and the other part staying constant and still have an equation. The only way this works is if both sides of this equation are equal to some constant value. The convention is that we're going to call that constant negative lambda, or the opposite of lambda. It doesn't matter. I guess that lambda should evoke thoughts of things that we've done previously in this course, but the real thing here, the only real idea is that it is constant. And then from there we can split the equation up. This is a three-piece equation. We can write it as two separate equations. So t prime of t over t of t equals minus lambda, and x double prime of x over x of x equals minus lambda. For this particular form, that first equation we can leave alone, but the second equation I'm going to do a little bit of work with. Rearranging the equation, I can write it as x double prime of x plus lambda times x of x equals 0. And this should look familiar to you. This is practically identical to the eigenvalue problem for boundary value problems that we looked at earlier in the course. Once we have the boundary conditions to go along with this boundary value problem, we can solve for the values of lambda, find the eigenvalues and the corresponding eigenfunctions. And then once we have the values of lambda, we can plug them in over here and figure out what's going on with t, which will be, relatively speaking, much easier. But there we have it. Looking at the clock here, I think this video has gone on long enough. I'm not going to actually go through and do that, but we'll wrap up as always with one for you to try. The problem that I looked at here was very similar to, I guess, a special case of the canonical form of the heat equation. So I'll give you one of the other canonical forms. How about Laplace's equation? Second partial of u with respect to x plus the second partial of u with respect to y is equal to 0. I would like you to use separation of variables to rewrite this equation as a system of two ordinary differential equations. You won't be able to do anything once you get there because you don't have the initial and boundary conditions. I guess for Laplace's equation, it's just boundary conditions. But take the time to get there, make sure that you understand the whole idea of separation of variables, and I'll see you in the next video.